Why do mountaintops feel like freezers when they're literally closer to the sun? It's one of those backwards little riddles that messes with your head, and the answer flips how you think about heat. Let's dive right in.
Let me ask you something that sounds dumb at first, but sticks in your head all day once you hear it. If you climb a mountain, you're getting closer to the sun, right? So why does it get colder up there? Seriously, shouldn't it be the other way around? You're gaining altitude, moving toward this giant burning star that blasts Earth with energy 24/7. That sunburn you got at the beach last weekend? That's from 93 million miles away. So climbing just a few miles higher should be like moving a little closer to a bonfire. And yet the higher you climb, the more it feels like someone left the freezer door open. Your breath turns to mist. Your fingers go numb. There's snow, there's ice, and the wind? The wind is downright rude. Meanwhile, back at sea level, people are sweating through their shirts, complaining about how their flip-flops are melting into the sidewalk. So what's going on here? Why does closer to the sun not mean closer to warmth? Let's talk about it. Because the answer flips everything you thought you knew about heat upside down.
So here's the brain bender. Climb higher, freeze harder. Like, Everest isn't a tanning bed, it's a giant popsicle maker, which feels backwards, right? Closer to the sun should mean hotter, not why do my toes feel like Legos in the freezer? Here's the twist though. Heat doesn't actually work the way your gut tells you. Let's listen to him.
Most people imagine that warmth comes from the sun directly heating the air. Makes sense, right? Sunlight hits your skin, and you feel hot. But here's the twist. The air doesn't absorb most of that energy. Sunlight passes through the atmosphere and hits the surface of the Earth. The ground, the ocean, the pavement, all of that absorbs the sun's energy and then re-emits it as infrared radiation. That's what actually warms the air around us. It's like the sun sends a package of energy, and the ground unwraps it, then shares it with the room. So when you're at sea level, you're standing in a thick, cozy layer of air that's being heated from below. But when you climb a mountain, you're moving away from that warm surface. The air gets thinner, the ground gets less effective at absorbing heat, and everything around you becomes really bad at holding on to warmth. Mount Everest is 5.5 miles tall. The sun is 93 million miles away. That means standing on Everest gets you 0.026% closer to the sun than if you were at sea level. It's like standing 1 inch closer to a bonfire across a football field. So, technically, yes, you're closer. But functionally, not even a little. Being closer to the sun does almost nothing to help you feel warmer. What actually matters is what's around you and how well it holds onto the sun's energy once it arrives. And mountains? They're not great at that. As you go higher, the air pressure drops, the molecules spread out, the density of the air decreases. And that has a strange consequence. Even if you don't lose any heat, the air feels colder simply because it's expanding. This is called adiabatic cooling. Imagine you have a balloon full of warm air. You let it rise. As the balloon climbs, the pressure outside drops, so the air inside the balloon expands. And as it expands, it cools. Not because it lost heat to the environment, but because it used that energy to expand. This happens to every air molecule in the atmosphere. As it rises, it cools itself down. So the air at the top of a mountain isn't just thin. It's naturally colder because physics made it that way.
And that's the big reveal. Your cozy warmth doesn't come straight from the sun, giving air molecules a suntan. Nope, the ground is basically Earth's giant heating pad, re-radiating energy like a smug middleman. Go higher and you're stepping away from the heater into thinner, lazier air that can't hold on too much. And the kicker? That adiabatic cooling trick is nature's way of saying, even if no heat escapes, rising air still chills itself, like self-sabotage, but with molecules.
Mountains are bad at holding heat. If you've ever stood on a snow-covered mountain under a blazing sun and still felt cold, here's why. Mountaintops are made of rock, often covered with ice or snow. These are poor materials for absorbing and holding heat. Snow reflects most of the sunlight that hits it. Rock absorbs some, but loses it fast once the sun dips low. And there's no moisture in the air to help trap any of that warmth. At night, any heat that was stored during the day disappears into space. There's no thick layer of atmosphere to trap it, like we have down in the valleys. So the temperature drops fast and hard. Mountains aren't ovens. They're more like giant granite mirrors bouncing the sun's energy back into the sky. At sea level, the atmosphere is thick, like a big warm blanket. There's more pressure, more molecules, and more interactions between them. That means more energy exchange and more warmth. As you climb higher, the blanket gets thinner and thinner. Eventually, you're not wrapped in warmth anymore, you're just exposed. The few air molecules that are left are too far apart to share heat effectively. It's like going from a crowded party to an empty warehouse. Same lighting, way less body heat.
Snow-covered peaks really are the ultimate trolls. Blazing sun, freezing toes. Snow just yeets the sunlight back into space like a giant cosmic reflector. And rock's basically the worst thermos ever. So when the sun sets, mountains dump their heat faster than a bad stock market. Down in the valleys, you've got the thick blanket of atmosphere trapping warmth. Up high, it's like someone stole the blanket and left you in a cold, echoing warehouse with zero body heat.
Need proof? Go to Kilimanjaro. Mount Kilimanjaro sits near the equator, one of the hottest places on Earth. The base of the mountain is tropical. You could sweat through your shirt by breakfast, but climb to the summit and you'll find snow, ice, freezing temperatures, same sun, same continent, same day. Altitude is the only thing that changed. Commercial jets fly at around 35,000 feet, higher than any mountain. And up there, the air temperature is typically minus 60 degrees Fahrenheit. Why fly there? Because the air is thin, which means less drag and better fuel efficiency. But it's brutally cold. That's why airplane cabins are pressurized and heated. Because outside that little aluminum tube, the atmosphere is just empty, freezing space. If the systems fail, you lose consciousness, and then you freeze, even in full sunlight. Space is even closer to the sun. Still cold. If being closer to the sun meant more warmth, then space should be a tropical paradise. It's not. Space is mostly a vacuum. No air, no molecules, nothing to trap heat. In space, if sunlight hits you directly, you warm up, but the side facing away, it freezes. There's no atmosphere to distribute or trap that energy.
Kilimanjaro really is nature's mic drop proof that altitude can beat latitude. You're practically straddling the equator, yet the summit looks like a freezer aisle. Planes at 35,000 feet, they're basically surfing that same thin, frigid air for efficiency. And space takes the logic nuclear. No molecules, no heat sharing. That's why astronauts can roast on one side and freeze on the other, basically cosmic rotisserie mode.
So you get extremes, blistering heat and instant frostbite at the same time. So no, closeness to the sun doesn't matter without the systems that hold the heat. Heat needs a team. Warmth is never about just being in the sun. It's about what that sunlight lands on and what kind of support system is in place to retain it. You need a surface to absorb sunlight, atmosphere to trap the heat, pressure to keep the molecules close, moisture to help store energy. At high altitudes, you lose all four. Mountains are stunning, but they are terrible at teamwork when it comes to heat. Let's zoom out for a second and talk about something big, something global, the greenhouse effect. At lower altitudes, especially near sea level, Earth's atmosphere acts like a giant thermal blanket. Sunlight comes in as visible light, hits the surface and bounces back up as infrared radiation, heat. But that heat doesn't just escape into space. Greenhouse gases like carbon dioxide, methane, and water vapor trap some of it and radiate it back down. That's what keeps our planet warm enough for life, and it's also why cities at sea level can feel like ovens during the summer. But up on a mountain, that thermal blanket is threadbare. There's less water vapor, less carbon dioxide, less of everything, really. The greenhouse effect still exists, but it's drastically weaker. So even if the sun is out in full force, there's nothing to catch the heat and bounce it back to you. It just slips away. You can actually see this effect at night. In cities, even after the sun goes down, the heat lingers. Sidewalks stay warm. The air holds its temperature. But in the mountains, the moment the sun dips behind a ridge, the cold creeps in fast. It's not just chilly, it's instant sweater weather. This is also why deserts, yes, deserts, can get freezing cold at night.
That heat needs a team line is perfect. Like warmth is basically the Avengers, and mountains keep firing their best players. No pressure, no moisture, no greenhouse gases, no cozy blanket. That's why cities roast long after sunset. Sidewalks hoard heat like grumpy dragons, while mountains drop temps the second the sun clocks out. Same reason deserts swing from broil to freezer at night. No team roster, just empty stands, so the heat leaves the game instantly.
The Sahara is at a low altitude, but it has incredibly dry air with almost no water vapor. So even though it might be 100 Fahrenheit during the day, it can plunge below 40 Fahrenheit after sunset. Same principle. No insulation means fast heat loss. Let's throw in another layer, literally. Atmospheric layers. The troposphere is the lowest layer of Earth's atmosphere, and that's where we live, breathe, and build our cities. It's also where weather happens. But here's the thing. Temperature decreases with height in the troposphere. It's a consistent pattern called the environmental lapse rate, roughly 3.5 Fahrenheit per 1,000 feet. Speaking of which, have you seen the Andes? Stretching along the spine of South America, the Andes run through countries near the equator: Peru, Ecuador, Colombia. You'd expect those places to be hot year-round, and at sea level they are. But go high enough, and you'll find glaciers, entire frozen ecosystems right in the tropics. All of these landscapes remind us that latitude tells you very little without context. It's not just how close are you to the equator, it's how high are you standing above the warm parts of Earth? Now here's a weird thought experiment. What if the sun were twice as close? At first glance you'd think everything would just be hotter. And yes, technically, the Earth would receive 4 times as much solar radiation. But the rules of atmospheric physics wouldn't change. Air would still cool as it rises. High altitudes would still be thinner. Heat would still be lost to space. So even in that hellishly warm world, mountaintops might still be cold, just cold relative to the burning surface below. And now let's really twist the idea. Look at other planets. Venus is closer to the sun than Earth, but it's not hot just because of that. It's hot because its atmosphere is thick with carbon dioxide, a runaway greenhouse effect. Temperatures there are high enough to melt lead. Meanwhile, Mars is farther from the sun and has a very thin atmosphere. Even in direct sunlight, it's freezing cold. So once again, proximity to the sun doesn't matter nearly as much as what kind of blanket your planet is wearing. The higher we climb, the colder it gets. Not because the sun loves us less, but because we've stepped beyond the shelter that makes life possible, the atmosphere that hugs us close, the oceans that cradle heat, the forests that breathe moisture into the sky. And it reminds us that life doesn't thrive because the sun shines. It thrives because Earth holds on.
So the punchline is almost poetic. Mountain cold isn't proof the sun's weak, it's proof our survival is built on layers. Blankets of atmosphere, oceans storing heat, forests pumping moisture skyward. Life thrives not just because the sun shines, but because Earth learned how to hold on to that gift. Strip that away, and even paradise turns into a freezer. YX really nailed this explanation. Sharp, clear, and fun. Links in the description if you want the full ride. And next time, let's just say we'll unravel another everyday thing that makes way less sense the closer you look. Stay nerdy.